Today we're going to be talking about curve sketching. And what that really means is we're going to be using our first and second derivatives to get an idea of what a curve looks like. So let's imagine this as if we weren't to have a calculator. This is what we would use to help us sketch curves. So what you need to be able to find when you're analyzing the graph is the domain and range, the intercepts, asymptotes, and symmetry. Those may or may not exist. And then giving me relative extrema and points of inflection. So we use our first and second derivatives for that. So you might want to pause the video and write those down if you need to. Our first example. And I have a few examples, so I apologize if this is a little bit longer of a video. I will be completely honest with you guys. The first examples that I picked were a lot more complicated than these examples. So I'm trying to kind of make sure it's a reasonable video for you guys. Okay, so this first example, x-intercepts. So if I make y equal to 0, and I get my x-intercepts, I'm going to factor out an x to hopefully kind of save me a little bit of room and a little bit of time here. And then I factor even more. So I get x equaling 0 and x equaling 3. Y-intercept, you make it 0, make it, meaning x's. There are no vertical or horizontal asymptotes. So now what I want to find is I want to find the first and second derivatives for increasing and decreasing. I'm going to be erasing as I go just because I don't have a whole lot of room on this slide. So I find my first derivative, which is 3x squared minus 12x plus 9. I set that equal to 0 and I factor as much as I can. And I'm going to go ahead and factor this completely. You might need to show more work than that. So remember, this number line is just a way for us to organize our work. This is not something that I will ever be looking at in terms of grading. So we have 1 and we have 3. So this is positive, negative, positive. And so I'm decreasing from 1 to 3. Remember, those are inclusive. We're increasing from negative infinity to 1 and from 3 to infinity. Now we find the second derivative. And I get 6x minus 12. Set that equal to 0. And we get x equals 2. So I'm going to do my number line right below this. And I'm going to line it up so that 2 is kind of on the number line where we see our derivative. And we are negative in there and then positive in here. So I am concave up from 2 to infinity. Now that is non-inclusive. Those are always parentheses. Concave down from negative infinity to 2. Now it's a matter of sketching our graph. And what I need to sketch the graph is I'm going to put in some numbers here. So I am going to find some values. I know there's a 0.00. I know that there is a 0.30. And remember, this is a touch and go. Remember this factored when I set it equal to 0 to this, which means that it's what I call a touch and go. It's a double root. So it kind of looks like a parabola at that point. We have 1. What I would do is I would plug in and I would find f of 1. And finding f of 1, I get 4. When I find f of 2, I got 2. So now it's a matter of sketching our graph. From negative infinity to 1, negative infinity to 1, I am increasing but concave down. So I am increasing, concave down. I'm now start decreasing, but I'm still concave down. Then at 2, I change my concavity, so I'm still decreasing, but I'm concave up. And then our graph eventually looks like that. Okay, the next example. Finding your y-intercept, make x 0, you get 0, 0. It's kind of nice if you realize that that's 0, 0. Setting this equal to 0, I am going to factor out an x to the 5/3. Remember, the exponents need to add, so you're subtracting 5/3 from this, and I'm left with x plus 5. So I have another x-intercept of 5/2 0. We have no vertical asymptotes or horizontal asymptotes because it's not a polynomial, but I don't have a rational function. I don't have one number over another. So now let's talk about finding our derivative. So finding our derivative. I bring down my exponent and multiply it so I get negative 16/3 x, and I reduce that by 1. Bring down the 5/3. And I set that equal to 0. And I am personally going to factor out a negative 1/3 x to the 2/3. So I factor out what the lowest exponent is. So I'm left with a 16x minus 25. So we have x equals 0 and 25 over 16. I wish that was a nicer number. I was kind of mad at the book for giving us that crazy of a number on this extra example they give the teachers. So I'm positive. Plug in 1. That might be the easiest thing for you to plug in. I'm still positive. And then I end up being negative on this side. Sorry, I couldn't find my notes. So now finding your second derivative. Again, bringing down, I get negative 80 over 9 x to the 2/3 plus 50 over 9 x to the 1/3 negative. So what I did is I simplified this. And I got a common denominator. So I get my critical points are 0 and 5/8. So luckily 0 matches up. 5/8 is somewhere in here because it's less than 1. Looking at my concavity, I am negative, positive, negative. So I am decreasing from 25/16 to infinity. I'm increasing. I don't have to worry about splitting that up, even though it's 0. You don't have to worry about splitting it up from negative infinity to 25/16. Concave up from 0 to 5/8. And I'm concave down from negative infinity to 0 and from 5/8 to infinity. Okay, so now graphing this guy. It would be nice if I could get some x value, some y values, but those are some crazy numbers that they gave us. Okay, so I'm just putting these x values down. And I mean, if you want to, you could plug those in, but I don't want to. I mean, we could, yes. So from negative infinity to 0, I'm concave down, but increasing. So I'm concave down, but increasing. But I have a vertical my derivative is 0 there. So you kind of have to make sure you have that. Then I start to be concave up to 5/8. So concave up, but still increasing. Then I turn to concave down, still increasing. Then concave down, decreasing. So that's how you would do one like that. Now the next example. X-intercept, let's do this one in green. X-intercept, make y 0, y-intercept makes x 0, you get 0, 0. Your vertical asymptote are whatever numbers make the denominator equal to 0. I just want to make sure you realize that those have to be lines, written as lines. Horizontal asymptote, look at the ratio of the leading coefficients. Or the ratio of the leading coefficients because the numerator and denominator are getting equally big as fast. Okay, so now getting your derivative. I am going to give you the derivative. Basically because I don't want you guys to have to suffer through simplifying. I would recommend that you find the derivative and then make sure that you agree with my derivative. So find the derivative on your own, and then this is one of the rare cases that I would want you guys to simplify. So I get that. So my critical points are 0 and plus or minus 5. Notice that plus and minus 5 is also a vertical asymptote. So I have negative 5, 0, 5, and this is for my first derivative. And then plugging in values, I don't want to bore you guys with that. Plus, plus, minus, minus. Finding your second derivative. Now, find your second derivative of that. Again, I'm not going to go through it because I'll be sitting here for 20 minutes simplifying. But find it on your own and make sure you agree with what I have. Now, I made this problem up. This is not one from the book. So hopefully I found my derivatives correctly. I think I remember double, triple checking them. And again, my critical points in this case are positive and negative 5. 0 is not a critical place. We don't have to worry about imaginary numbers. So I am positive, negative, positive, and this is for my second derivative. So I'm decreasing, now this is key, I'm decreasing from 0 to 5. 5 is not in the domain, so I have to break this decreasing up. And then 5 to infinity. 5 is not in the domain, so I have to break that up. Negative infinity to negative 5. And there's parentheses because 5 isn't in the domain. Or negative 5 in this case. Concave up. I am concave up from negative infinity to negative 5. And also from 5 to infinity, concave down from negative 5 to 5. So now it's just a matter of getting my graph. Okay. Y-intercept, excuse me. Horizontal asymptote is 1. Vertical asymptote. The other vertical asymptote. Y-intercept is 0, 0. So I know that when you've learned these in your other classes, you probably chose some points and figured out if you're positive or negative to figure out where you're at, if you're up here, down here, stuff like that. And you could do that. You're more than welcome to do that. If I plugged in any number in between here, so like say I plugged in negative 1, I definitely would be negative, so I know that I'm below, and I know that I don't cross. And in general, if you end on one side of your asymptote down, you're going to start on the other side up at the very top. And down, start up top. Now let's just make sure our graph makes sense. I'm decreasing, I'm increasing from negative infinity to negative 5. Yeah, that makes sense. And increasing from negative 5 to 0. Yeah. Decreasing from 0 to 5. And then still decreasing. Now let's look at our concavity. Negative infinity to negative 5, I'm concave up, yes. And concave up there, yeah. And then concave down there. Okay, hang with me. One last problem. And I'm going to do this one very similar to what I did with the last one. So keep in mind here that this is a sine and cosine, so it has a period to it. And everything in this case repeats every 2 pi. Your x-intercept set y equal to 0. When is the sine equal to 0? Well, that's at multiples of pi. I'm just going to give us 1. Y-intercept, you set x equal to 0. And it works out that there is none. Your vertical asymptotes are when the denominator equals 0. So that happens at 0, 2 pi. We would also have another one here. We would have what I was just thinking is that I was thinking we had one at 0, 0. But if I plug in 0 here, I get 0 over 0, which we know can't happen. So that's why I have a vertical asymptote there. That's what kind of caught me on this one. Horizontal asymptote. So since sine and cosine oscillate, there is none. They kind of act the same. I'm going to do what I did with the derivatives for the other one, for the previous example. Finding my derivative here. My derivative, use your quotient rule. Practice your quotient rule. I'm going to give it to you guys. So here my critical points are 0 and 2 pi. And I'm only going to graph this for part of the period. 0 and 2 pi. Notice how cosine never goes higher than 1. So I know this number is always less than 1. So no matter what, this denominator is always positive, times by a negative, we're always decreasing. I'm never increasing. Now finding my second derivative. So do your low D high minus high D low, draw a line, square the below, simplify that out. You guys need that practice. I don't need that practice. I'm more than willing to go through those with you guys in class and maybe even remind me. I'll have it up on the sideboard for you. So we get this. Now our key points are, I wish that was lining up a little bit better, 0, pi, and 2 pi. Getting the signs of my second derivative is negative, positive, negative, positive. So I'm concave up from 0 to pi, and I'm concave down, and from 2 pi to 3 pi. And remember, it keeps repeating every 2 pi. So my concave down is from negative pi to 0, and then pi to 2 pi. Now, I just noticed I have a little mistake here. It's decreasing for all x in the domain of f of x. Remember, we have some vertical asymptotes happening here. So let's graph this guy. Now, when you're graphing, I know some teachers like you guys to graph things a little bit differently. I want an x and y axis drawn in. I know some teachers don't draw that in. I want that drawn in. And please don't use the excuse of my teacher last year didn't want us to do that, because I want you to do that. I'm your teacher this year. So draw in your asymptotes, your vertical asymptotes. Remember, they're repeating every 2 pi, so once I get one of them, you know where the other ones are going. X-intercepts happen at pi and a negative pi, since our period is 2 pi. So I did have another x-intercept. And remember, they always repeat. So I'm decreasing. So from negative 2 pi to pi, I'm decreasing. Actually, no, let's look at from negative pi to 0. I'm concave down, but always decreasing. So concave down, decreasing. Here I'm concave up, increasing. I know that looks kind of funny. It's supposed to look like an x cubed graph. And since it's periodic, they repeat. So once you get the idea of what one of them looks like, you get the idea of what they all look like. Okay, I know that was a long video. I apologize. There's a lot in that. Please make sure that you've watched and paid attention for more questions in class.